all of you for sticking with it. That is so great. Where do we stand, right? So in my first lecture, I was talking about the concepts of what is a liquid crystal order parameter. How do you define the tensor parameter, order parameter, what do we average? Right? In the second lecture, I moved on to the free energy as a function of the pneumatic order parameter and showed you how to do mean field theory. Right? And so that establishes where is the isotropic pneumatic transition. That is, at what temperature is the isotropic pneumatic transition. And how big is the pneumatic order parameter as a function of temperature in general. Right? Today I'd like to do two things. Right? So first is to continue talking about free energy in terms of both the magnitude and direction of the pneumatic order, and show you how various theoretical concepts sort of link together. And then the second thing is to talk about chiral phases, what happens when there's chirality and how a chiral system can become frustrated. So, to begin with, about the free energy, right? In the previous lecture, I was more specific. That is, I was thinking of a specific model for what's the interaction between molecules, and given that model, how to extract a prediction for the pneumatic order parameter. Now, I want to just briefly show you an alternative view, which you may or may not have seen, of Landau theory for phase transitions. And, you know, the Landau theory, this is what I like to call, how to get something for nothing, right? So, you know, everyone in the world wants to get something for nothing, right? I mean, if I'm in a Chinese supermarket and they have samples of chicken feet, I think, well, if it's free, I want one, right? And so, you know, that's what everybody wants, and so that's what Landau theory achieves, right? And so here we could say, suppose that we don't know anything about the microscopic structure of the world, right? Suppose we don't know that the world is made of atoms and molecules and so forth, right? All that we know is an order parameter, right? So we just say there's an order parameter with some symmetry, and we want to construct a free energy based on that order parameter to describe a phase transition, right? So how could we do anything, right? Landau's idea, really kind of a brilliant insight, is that the free energy function must be an analytic function, right? So that's a concept of complex analysis, but basically it means a smooth function. It's something that can be expanded in a power series, so that there's no singularity as the input into the theory. There can only be a singularity at the phase transition as the output of the theory, right? But we want to see how a theory can have a nice smooth input and a singular output. Okay, so how would we do it for the Ising ferromagnet, right? So a ferromagnet where there's an order parameter m, and we think that there should be a symmetry in the energy, right, between the magnetization pointing up and the magnetization pointing down, right? That those are two different states that should have the same energy, the same free energy. Okay, so that's one bit of information if we wanted to make a theory of magnetism without really knowing anything about magnetism, right? And then another bit of information would be that near the transition m must be small. So with this idea of smoothness, we would expand the free energy as a power series in m. And because of the symmetry, we can have only even powers, right? So we would say that the free energy is like a constant plus m squared plus m to the fourth, okay? And let's stop there because we think m is pretty small, okay? And then we can ask, well, where's the minimum of this function, right? Is it going to be at m equals 0 or at m not equal to 0, right? Well, if the coefficient a is positive, well, let me back up. The coefficient b better be positive if we're going to truncate the series here, right? Because if it isn't, then the results are going to go crazy, right? Because then m will just go to plus or minus infinity, and the free energy will go to negative infinity, and the whole thing will be unstable, right? So this b better be positive if we're truncating here. Okay, if b is positive and a is positive, then this is the free energy is just going up, right? The minimum's at m equals 0. On the other hand, if b is positive but a is negative, then the free energy starts at some value at m equals 0, goes down, and the m squared, then it goes back up again from the m to the 4th. So then the minimum must be at a non-zero value of m. Okay, so in that case, we could say if something special happens at a equals 0, and something special happens at the transition temperature, so let's say that a is some coefficient times t minus t0, and b, well, you know, probably changing as a function of temperature, but not so much, close to the transition. So let's put in that it's a constant near the transition with respect to temperature. And then if we minimize, we get this solution for A. And this is actually, well, it doesn't tell us everything, but it's kind of a miracle that it tells us anything, right? That it tells us the behavior of the magnetization close to the transition within this mean field approximation. Not exact, but within this mean field approximation. And it shows how we get this kind of plot where m as a function of temperature is 0 at high temperature, and then it increases as a square root law, like that. Right? We could put a field in on top of that as well. Okay, so that's how we would do it for a ferromagnet. For the pneumatic, similar kind of story. Now we're working in terms of this tensor order parameter. And we have a rotational symmetry, right? That the model has a higher symmetry than the final state, right? That's how Mark would characterize it in his lecture. So in the model, there should be full rotational symmetry, that this tensor could be ordered in any old direction, and so the free energy better have only things that are rotational invariants. Well, what's a rotational invariant? Well, like the trace of a matrix, right? The trace of a matrix is the same as you rotate the coordinate system. So we could put in things like the trace of q squared, the trace of q cubed, the trace of q fourth, and so forth, right? And then relate that to the scalar order parameter s. Okay, and you'll note that this is similar to what I had for the ferromagnet, but it's not exactly the same because now there could be a cubic term as well. Okay, and so then when you look at the characteristic shape of the free energy, just based on expanding that, can I have the lights please? The shape of the free energy with the cubic term, it is something that can start off like this and just keep going up, or it could come down like that, or down like that. And so here we would say there's an isotropic state, and it can have a metastable pneumatic state, or a first order transition from isotropic to pneumatic, and then at a lower temperature down to this kind of behavior where the pneumatic state becomes stable. Right? So this is the same kind of behavior that came from the big Meyer-Zalba calculation that I showed you a couple of days ago. It gives the same kind of result, that there's a first order transition from isotropic to pneumatic. But the amazing thing is that we barely put in any assumptions, right? Only something about the symmetry of the order parameter. Okay, so that's this alternative point of view of Landau theory as a way of getting out a free energy that is a function of the order parameter, depending on the symmetry of the order parameter. Was there a question in the back?
So I was just wondering, maybe I missed this, but is there a reason not to include gradients just for...
I'm about to get to that. Thank you. Yes. Thank you. Excellent segue. Right, so now we can say, what about the orientation of the order parameter, right? And so the kind of free energy that I have so far, right, depends only on the magnitude of the order parameter and not on the direction of the order parameter. And people often make the analogy with a Mexican hat for the shape of this potential, right? So here, actually, I don't actually have a Mexican hat. I have kind of a safari. Okay, so here's my shape of the potential. Okay, so this is a three-dimensional plot, right, where the z-axis is free energy, okay, and then the horizontal plane, right, represents the order parameter space, right? So going out from the center is the magnitude of the order parameter, and coming around this way is the orientation of the order parameter, right? And so what you can see is that there's this characteristic shape of the free energy, right, as a function of the magnitude of the order parameter, say where there's a minimum out here at some particular value of the order parameter. But the free energy is constant with respect to direction, right? That all of these states around this circle are equal in free energy, right? So the free energy there doesn't care about the direction of the order parameter, but it does care if the direction is changing from position to position, right? That, everybody pointing this way is the same as everybody pointing that way, but if some are pointing this way and some are pointing that way, that costs free energy, right? So there could certainly be a dependence of the free energy on gradients of the director, or gradients of this full tensor order parameter, just as the question asked, right? So how would we include that in the theory? Well, let's continue to follow the inspiration of Landau theory by constructing terms that are allowed by symmetry. Okay, so step one in that, right? We could say, suppose that the system is not chiral, that it has symmetry under reflection or inversion, right? If it's not chiral and it's not polar, then you can work out that all the terms that are linear in first derivatives are forbidden by symmetry. But there can still be terms that are quadratic in the first derivatives, right? So here is an example of a term that is quadratic in first derivatives, right? So this is derivatives of q beta gamma with respect to coordinate alpha, right? And contracted over alpha, beta, and gamma, right? So reminding you of tensor algebra, right? When an index is repeated twice, it's implicitly summed over, right? So this is a sum over alpha goes from x, y, or z. Beta goes x, y, and z. Gamma goes x, y, and z, right? So this is 27 terms right here. Okay, and so this is an example of a gradient squared term. And if we put in the relationship between the full tensor and the director field, right, then this reduces to this expression in terms of derivatives of the director field. Okay? So this now is the simplest version of the Frank free energy, right? This is seeing how the Frank free energy comes out of this free energy in terms of the full tensor order parameter, right? Now, some of you might be thinking, right, what am I talking about? Because the Frank free energy doesn't look like that. The Frank free energy looks like this, right? And so this is a more general version of the Frank free energy, right? This is a more general version that encompasses the fact that there are distinct modes of distortion for a pneumatic liquid crystal that are the splay, twist, and bend. Right, splay looks like this, twist like that, and bend like that, okay? And in general, those things don't have to have the same elastic constant. They could have somewhat different elastic constants. And they do have different elastic constants. People measure them in the lab, but they're not that different. And so it often happens that people will make approximations that they're all about the same. And if they are the same, then this combination of derivatives reduces to this kind of expression, except for surface terms I don't want to talk about. Okay, so far so good. So, now, once you've got the Frank free energy, what can you do with it, right? Well, I mean, in some sense, that's what we've been hearing about for this whole school, and we'll continue to hear about for the rest of this school, right? But one point of this, right, is that if you have a bulk pneumatic phase with no fields and no boundaries, then the minimum of the free energy is kind of boring, right? The minimum of the free energy is just to have all the director at all positions pointing in the same direction, which could be any direction in three-dimensional space. Okay, so that's simple enough. If there are conflicting boundaries, like I can draw it here, can I have the lights again, please, Kristen? If there are conflicting boundaries, if you had some cell with, say, hybrid alignment, like that, so that it's homeotropic on the bottom and planar on the top, then there would have to be some profile of the director as a function of position, where it would be gradually rotating over like this. And minimizing the free energy would allow you to calculate the director field as a function of position, right? And then, you know, if you have a pneumatic with boundaries, some kind of boundaries, and then some applied electric or magnetic fields, then you get, you know, very rich behavior, like the Frederick's transition, you get switching, you get the whole LCD industry, right? So these are sort of standard stories in liquid crystal science and technology, which maybe some of you have heard, and if you haven't, they're great stories. You should go learn them. But I want to talk about something different for the rest of this lecture. What I want to talk about instead of that, right, is how to get richer systems just in the bulk, right, not specifically with boundary conditions or that kind of thing. And one way to get richer systems in the bulk, you know, as you've already heard about from some of our speakers, right, is going to have chiral molecules, right? So chiral molecules being molecules that do not have any reflection or inversion symmetry, right? They are not equivalent to their mirror images. And so the main effect of this on liquid crystals right, is that chiral molecules don't tend to pack parallel to their nearest neighbors, but at some slight angle with respect to their nearest neighbors, right? So that some position, they'll be pointing this way, somewhere else pointing this way, and so forth. Okay? So that it favors a macroscopic twist in the orientation of the molecules with some characteristic chiral length scale. So one way to think about that is that if you have chirality mathematically, it allows a new term in the free energy. Right? It would allow a term that looks like this Q0 term. Right? This is a term which is related to chirality. If you multiply out this square, right, you would see that there's a term that is linear now in the first derivatives of the director field. It is just this n dotted into the curl of n, right, which is linear in the first derivatives. And that changes what's the lowest energy state of the model. Right? The lowest energy state of the model is now no longer the thing that has a uniform director, but instead it has this helical modulation of the director field, right? Where the director field here is pointing in some direction, and then as you go along the helical axis, it's twisting around. Okay. And so I imagine that you've seen this kind of configuration before, and some of our previous lectures have been talking about cholesteric liquid crystals. But there's one feature of this that I really want to point out to you, okay? And that is that the Frank free energy for this configuration is 0. If you take this configuration and you put it into the Frank free energy, it's identically 0. And 0 is as good as this thing can ever get, right? That, this is, of course, the sum of squares, right? And so a sum of squares can only be 0 or positive, right? And so the helical configuration of the director is an ideal configuration for this, right? It is exactly minimizing the free energy everywhere, right? So I would say, in that sense, the cholesteric phase is like the luckiest phase in the world, right? Because it gets exactly what it wants everywhere, right? So, when was the last time you wanted something complicated and you got exactly what you wanted, right? I mean, it doesn't happen that often, right? And it doesn't happen that often for phases either, right? Phases generally are not able to achieve complicated modulated configurations everywhere, right? But the cholesteric does. That question is.
So this helical configuration with Frank free energy, which is 0, does it mean that the system is in ground state or is not frustrated or what?
Both, yeah.
Both, okay.
Yeah. The system is in its ground state, right? This is the minimum of the free energy. So it's the minimum of to say it's in the ground state means it's the minimum of the free energy integrated over all space, right? But not only is it the minimum of the free energy integrated over all space, right? But it's also the minimum of the free energy density at every position, right? And that's a stronger statement, right? And there are lots of situations where that's not possible, right? As I will show you, right? So the general phenomenon where that is not possible, right? Situations where that is not possible are called frustrated systems, right? Frustration is the phenomenon where there is some local ground state that is not achievable everywhere, right? So the classic example of frustration that lots of people begin with is in an anti-ferromagnetic system, right? So if you have an anti-ferromagnet, that's something like the Ising model that I showed you previously, except that the interaction is the opposite. It favors opposite spins on neighboring sites like that. That's the anti, is that it has a plus sign here instead of a minus sign, right? So that it favors having nearest neighbors that are pointing in the opposite direction, right? So if you have this kind of system on a square lattice, well, that works great, right? You can have an alternation like this. Everything is ideal, right? Every site has its favorable configuration with respect to its neighbors, right? So this is not a non-frustrated, an unfrustrated system, just as a cholesteric phase is a liquid crystal that's not frustrated, right? But if you have this on a triangular lattice, okay, so we have, let's put the up and down spins here, right? If you start at one point, if this is going up, and this one's going down, and now you get to this, and it says, wait a minute, I've got a problem here, right? I have a problem because the interaction with this site tends to favor up, favor down, and the interaction with this side tends to favor up, right? So that there is a confusion, right? You know, like a child that having the mother tell him to do one thing and the father tells him to do something else, right? And so this system does have a global ground state, right? There's some state that is the minimum of the Hamiltonian, but it's a more complicated state, which is not the local minimum for all the different pairs of spins. So let me show you how something like that can happen in liquid crystals as well, right? So here, suppose that you have the cholesteric phase in a magnetic field, right? So you have the Frank free energy like this with the chiral term, and it favors a twist in the orientation like that. And then there's a magnetic field, say pointing in the vertical direction, which tends to favor a uniform director field aligned with the magnetic field like this. Okay, and so now there's this kind of competition between these two effects, right? Leading to a frustration where there's no configuration that ideally satisfies both of these things, right? And so what happens as we tune between a state that's dominated by chirality and state that's dominated by the magnetic field, right? Well, in an experiment, that would typically be done by starting with this chiral system, right, and gradually tuning up the magnetic field, right? Theoretically, I want to think about it in the opposite direction. I want to think about, say, let's take this uniform system under a magnetic field and gradually tune up the chirality parameter, which, would correspond to putting more chiral dopant into the system, which is not a normal experiment to do, but, it's just a different way of moving through the phase diagram. Okay, so what do we do then, right? Well, we could say, let's write the director in terms of some angle, theta of x, okay? And then we can work out the free energy in terms of theta and its derivatives, okay? And if we arrange the terms like this, then the first part shows the ground states that are favored by the magnetic field, right? The ground states at theta equals pi over 2, 3 pi over 2, 5 pi over 2, etc., right? All the states could be putting like this, or that, or that, or that, right? That's a whole series of states that are all ideal as far as the magnetic field goes, okay? And then this term shows a favored twist from one ground state to the next, right? The chirality is favoring this kind of a twist, okay? And so, if you have a system that's mostly dominated by the magnetic field, and then you put on a slight tendency to have some twist, what can it do, right? Well, it could make a state where it is mostly in the direction favored by the magnetic field, and then whoosh, some sudden twist, right? Then mostly in the direction of the field, and then another flip, right? So that it would have these steps in the orientation, right, of theta. So if I wanted to make a plot of that, kind of lights again, thank you. If I wanted to make a plot, I could say, let's plot theta of x as a function of x. And so it would be, say, at pi over 2, and it's roughly constant there. And then rapidly, but not discontinuously, just rapidly, changes from pi over 2 to 3 pi over 2. And then up here to 5 pi over 2. And so forth. Okay? And there's an exact solution for the shape of theta of x when there's just a single one of these domain walls, okay? But, the shape of that is this kind of a form. This is an inverse tangent kind of a shape. Okay? And so here you see a sort of behavior emerging from the theory, right? This is ICAM, so we talk about emergence, right? ICAM likes emergence. And so we see a behavior emerging from the theory, right? That the theory is making these walls, which could be considered solitons. Right? This is a soliton-like behavior coming in within the liquid crystal, right? That comes from the competition between these two things. And it's a very general sort of phenomenon. Like that frustration is leading to complex configurations that have some natural length scale, right? They don't just spread out. They have a natural length scale and a natural energy, and they can act a little bit like particles, right, that are localized. So you've seen more complicated examples of this sort of phenomenon already in the school. In Ivan's talk, for example, right? These torons that Ivan speaks about are much more complicated and interesting structures, right, that emerge from the competition of different influences which are not compatible with each other in a liquid crystal. But here I just wanted to sort of distill it down to the bare minimum for you to see that, a little bit of this phenomenon with a kind of minimal mathematical model. Okay, so here is an example that with the same calculation, right? Here's a visualization that shows that when the magnetic field dominates, you get this nice uniform state. When you have more of the twisting influence, you get a single domain wall. And when you have a lot of domain walls, the whole curve gets smoother and it evolves eventually to this nice uniform looking helix, just like the ordinary cholesteric phase that you know and love. Okay, so the general principles to draw from this, like mini examples, right? One, that the competition between chirality and the aligned field is resolved by the domain walls or solitons. That the domain walls take the system from one domain to another equivalent domain. That's like what Mark Boak was talking about, right? When he lectured about domain walls, right? That the system has multiple ground states, and a domain wall separates one ground state from another, right? Here, my system has ground states where theta is pi over 2, 3 pi over 2, 5 pi over 2, right? And here you see explicitly a domain wall between those things, right? And hence, getting a more complex structure than would be expected from either the chirality or the field. Okay, now, maybe you think this is something special that happens just because there's an applied field, and it wouldn't happen just from geometry alone. Wrong. It can happen from geometry alone. Let me show you another mini example that shows where geometry does it. Okay, so what would happen if you have a two-dimensional chiral liquid crystal, right? So it would be, I could be thinking either of liquid crystals in the two-dimensional universe, or I could be thinking of liquid crystals in a thin film on the substrate. Okay, and in that case, if you have chirality, you would expect to get some kind of twisted configuration. What's twist? Well, if you have symmetric C, right? Then if you have a modulation like that, that's a three-dimensional twist of the director field. Okay, so let's try to make it with no defects. Okay, so if we try to make a chiral configuration with no defects in the two-dimensional liquid crystal, then you would try to draw something like this. You say, I've got a theta that's initially, minus pi over 2, and I'll make it just increase up here to 0, pi over 2, and so forth, right? So here it's going around a full circle, right? So you think this is chiral, right? No, it's not. It's not chiral because this region and this region are exactly mirror images of each other. Right? There's a mirror plane right there between them. Okay, so this is not a chiral configuration, right? The chiral terms in the free energy do not favor this sort of thing, right? So what is the global minimum when you have chirality, right? Well, I've got this sort of mathematical argument that the chiral term in the free energy could be written like this, as the derivative of the y component of the director with respect to x. And so, the way that you would try to get the best negative contribution to the free energy, right, coming out of that, would be to have the y component increasing as a function of x. But hey, it can only increase from -1 to 1. That's as far as it can go, right? So, how much of a negative chiral influence in the free energy can you get? Only this much for a single domain. But if you could just break the system up into finite domains separated by domain walls, then you could get this nice favorable contribution to the free energy over and over again. So, the domain walls would cost free energy, but maybe they wouldn't cost as much free energy as this provides a benefit. Okay, so the minimum of this free energy turns out to be a structure like this, right, where there is a two-dimensional modulation of the director field, where it rotates through some angle, and then there's a domain wall, and then it can rotate through that angle again, and another domain wall, and so forth. And then the free energy is the favorable contribution coming from chirality plus the unfavorable contribution coming from the Frank free energy plus the unfavorable contribution from the domain wall energy itself. And you can minimize that, and as long as the favorable contribution from chirality is big enough, it will favor some domain wall spacing, like this, right? So some net density of domain walls, right? And get a periodic system that's sort of analogous to the more complex periodic systems that you've seen from Ivan and other people through this school. But coming just from this geometric frustration of not being able to have a perfect chiral configuration in 2 dimensions. I want to make one more point to you that's sort of a general lesson about different ways of thinking about defects. Right? So my general point is, right, that this is a kind of macroscopic view of what's happening in the structure, right? This is a macroscopic view where we say that these boundaries are lines, defect walls, and we say, we've got some energy per unit length, and that's just a feature of the theory, is that there is a wall, there are these walls. We could also take a more microscopic point of view, right? We could also work on a more detailed theory that describes what's happening inside of the walls, right? So, I'm going to skip that. Okay, we could say there could be a domain inside the domain walls. Maybe the magnitude of the molecular tilt is changing, right? That if you think now of the director field as not something with a fixed magnitude of molecular tilt and only a variable azimuth, but you could let the magnitude change, the magnitude go to 0, or even just get reduced, right? Then you could construct a theory where there's a domain, say with a big magnitude of the molecular tilt, and then a wall with a reduced magnitude of the tilt. And then that keeps repeating, that kind of alternation. And so this is one way of getting a theory, a more detailed theory that describes the domains and the walls, right? And then it could predict what's happening within the wall itself, right? Now, there are pros and cons between these two kinds of theories, right? One advantage of the macroscopic theory, well, I mean, of course, it's easier to do macroscopic theory. Another advantage of the macroscopic theory is that it's more general. It could apply to lots of kinds of systems where there are different kinds of behavior happening within the defect lines. But the downside is that it is not giving us any information about what's in the defect lines, right? Whereas here, this is a more specific microscopic model that gives one model for what could be happening in the defect lines. Now, of course, there could be other models for what happens in the defect lines. We could say maybe you have some two-component mixture of liquid crystals, and then the domains would be regions with the optimum composition, and the domain walls would be places with some different composition. Or we could say, suppose you have a mixture of liquid crystals and quantum dots, right? Then the domains could be regions that expel quantum dots, right? And the domain walls could be regions with a high concentration of quantum dots, right? And that could be our model for what happens within the domain walls, right? And that's what happens experimentally in one of our talks from this morning. So in general, the principle is there could be any different microscopic structure for the domain walls compared with the domains themselves. So these now are two sort of mini stories about how you get frustration occurring in different kinds of systems, and it's meant to provide different ways of thinking about defects and different levels of theories. And I want to emphasize that this provides a sort of simple view on things that you've been hearing from various lectures, right? So, for example, in Mark Bowick's lectures, right, where he speaks about a set of ground states, right? Let's think about the set of ground states, right, in terms of the hat potential, right? So when Mark says, for example, that if you have a 2D ferromagnet or a 2D pneumatic liquid crystal, right, that there is a set of ground states that is S1, right? So that's a set of degenerate ground states, equivalent ground states. The system could be in any of them, right? Well, here I'm going to draw them on the hat, right? That's this set of points, right? Sure, right? That's this set of points. This is S1, okay? And that is, a correct description in the more macroscopic type of theory, right? A macroscopic type of theory that says that the magnitude of the order parameter is fixed, right? Now, if you were to go to a more microscopic type of theory, you would be saying, well, there's not just this set of states, there's the whole hat full of states, right? There are all these other states with different magnitudes of the order parameter, okay? And then with those different states, right, the states with different magnitudes of the order parameter are suppressed because they cost more energy, right? How much more energy? Well, this much more energy, right? The hat is an energy plot, okay? But they could still occur in some tiny little regions at the core of the defect, right? And so if you have a domain wall, it could be a place where the system is going over a hat like that, right? Or if you have a defect line in 3 dimensions, right, where the order parameter wraps around the line, means you have the order parameter going around like this everywhere outside of the defect line. But at the tiny core of the defect line, like the 10 to the minus 27 centimeters for cosmic strings, right, or somewhat larger than that for liquid crystals, you have this kind of value for the order parameter. Because the gradient energy, right, for having a gradient of this direction in a region of 10 to the 25 centimeters is okay, right? But if it gets down to 10 to the 27 centimeters, the gradient energy is so big that it exceeds this energy penalty for going to this place on the hat. And so the order melts. It puts you here on that. Right. So this provides a way of thinking about a whole bunch of things. And I guess the most common kind of situation where liquid crystal people run across this sort of behavior is in the context of blue phases. I imagine lots of you have seen stories about blue phases. You know, we haven't talked about them in this school really, but in other kinds of conferences you might have attended. These are very complex three-dimensional structures where there is a sort of biaxial double twist configuration concentrated in tubes, right? But the tubes cannot get arbitrarily big. The tubes are limited in how big they can grow, and then they have to have defects, right? But if the favorable energy associated with the tubes is big enough, it might be worth having the defects in order to get that favorable energy. And so indeed, these things form. They can form with periodic arrays of the non-defect tubes surrounded by defect boundaries. These are typically arranged in square lattices in either the configuration of blue phase 1 or 2. And so they make very complex structures, but they really do form. And people even now have schemes for how to use them in liquid crystal displays. Okay, so this is the main story that I wanted to present to you for today. And in the lecture tomorrow, I want to show how related kinds of things can happen that are not driven by chirality, but driven by polarity instead, leading to other kinds of phases, especially twist-bend phases, that are subjects of very recent study. But I think I want to stop for today and see if there are any questions that I can answer for you. Please.
Apart from being able to include details about the distribution of the fields in both sides of the domain, or is there anything that you gain from modeling the system from a microscopic perspective?
From the more microscopic description. I guess what you would gain would be a description of both the size of the domain wall and the energy of the domain. Those are the two main things that come out of that, right? So if we go back to the cholesteric in the magnetic field, right? Here, there is an exact solution, right, for theta of x. And if you do the exact solution, you can learn two things, right? One is that you get this correlation length, right, in terms of the magnetic field and other parameters. And that correlation length is the width of this region, okay? So this is what corresponds to the 10 to the 27 centimeters for the cosmic strings, right? It's saying if you're outside of this width, you have what looks like a nice non-defect region, but inside this width, it looks like the defect, right? And so the microscopic model tells what's happening inside of there, right? And then the other thing is, right, if I take this profile, theta of x, I can plug it into the free energy, right, and say, well, what is the free energy of this compared to the free energy of a state where, say, I just have theta equals pi over 2, right? And take that difference and integrate it across the whole width. And so that gives the domain wall energy per unit length or unit area. So in that sense, we don't have to introduce it as an extra parameter of the model. You know, it's coming from more microscopic parameters. So those are the two kinds of benefits from doing the microscopic theory, I'd say. One other point I would make, I guess, is that you know, what's microscopic or macroscopic is a relative thing, right? That a theory can be microscopic compared to one thing, and macroscopic compared to something else, right? And so, for example, you know, if you go back to the, if anybody noticed the question I tried to ask Mark after his talk, right? So, you know, Mark was telling us stories about both a three-dimensional nematic and a two-dimensional nematic, right? So in the three-dimensional nematic, right, the director can point anywhere in three-dimensional space. Right? The two-dimensional nematic, the director is confined to the XY plane. Right? So I was proposing an intermediate state, right, where you take a liquid crystal with a negative dielectric anisotropy, right, and put on a field in this axis, right? So a negative dielectric anisotropy means that the director is repelled from the field direction, okay? So if there's a really strong field, now the director will be confined to 2 dimensions. If there's a weak field, the director would like to point mostly in the XY plane, but it's kind of a weak preference to point in the XY plane. Okay? So, in that situation, I would say the three-dimensional theory is acting like the microscopic theory, right? But if you think of that, then you would say, well, there could be a situation where there's one region where the director is pointing like this, and then it flips over and points like that, right? And so there's a domain wall where the director does the bad thing compared to the electric field, right? And so then the three-dimensional liquid crystal theory would be playing the role of a microscopic theory, and the two-dimensional liquid crystal theory would be playing the role of the macroscopic theory that works on length scales bigger than the width of a domain wall, right? And so these are relative things.
One more question?
So I was wondering, in thermal systems with certain fluctuation length scales, if you introduce confinement, then that sort of gives rise to interesting forces and these kinds of things. So I was wondering if you here have some liquid crystal system with certain inherent correlation lengths, and you begin confining it to sort of the order of those domain sizes, do similar interesting effects arise?
Yeah, I mean, everything that I've done here involves minimizing the free energy, right? So neglecting those fluctuations, right? But if you were to put in fluctuations, then yes, by all means, they would occur at non-zero temperature. Those fluctuations, could be treated in either the more microscopic or macroscopic point of view, right? So, for example, if we have a structure like this one, okay, so if this is the ground state, right, minimum of the free energy, you could take the point of view, at this level of description, right, where I have directors everywhere here, and then there could be fluctuations in the director field that have the director field wiggling back and forth, right? Alternatively, we could go to even a more macroscopic view than this, right? Suppose we tune out to a more macroscopic view where all we could see are the walls themselves, right? For example, maybe there's a bunch of quantum dots mixed into the system, okay? And the quantum dots tend to preferentially accumulate along the walls, okay? So when we zoom out, all we can see are bright lines associated with the quantum dots, okay? Then, when there are thermal fluctuations, these lines would not be straight, right? They'd be fluctuating around somewhat. So this might look like a bunch of, polymers, right? Each of these lines would be sort of worm-like. And so you could regard them as a parallel, or approximately parallel polymers fluctuating, and do the statistical mechanics of those kinds of fluctuating objects, right? And presumably, if you were to do the calculation both ways, you would get the same answer for things like how big are the lateral fluctuations of these lines. And so, yes, that would make a nice comparison.
But I think there's a difference we make between the length scale of typical fluctuations and the length scale of domains in these typical systems. Is that right? The
Yeah.
domains are much larger than the typical scale.
The domains are much larger than this width, right? So that's the microscopic versus macroscopic that I already presented, right? Is that there are these narrow walls compared to the big spacing between the walls, right? But then if you go to yet more macroscopic, right, then you would be worried about things like, how straight are these, right? What's the persistence length of walls like that? So that the sort of polymer physics questions that we've been hearing about from some of the other talks would come into play there. So this macroscopic versus microscopic, it's a whole scale that you can walk up or down, right, depending on what you care about in any particular problem.
Thank you very much.
All right, thank you.